Hello linear algebra students. Let us begin module 10 for week 10. Scalar products and orthogonality. What is a scalar product? A scalar product is an abstract binary operation from V2 to R. So it's a double variable map. We're not starting from V, but we are starting from V2. So we need a pair of vectors, V, W. And then what pops after that? Look at the target, it's a scalar. So we put two vectors in and one scalar pops out. And furthermore, we have to have these four properties: symmetric, bilinear 1 and 2, and positive definite. In short, a binary operation from V2 to R that satisfies these four conditions, SP1 through SP4, is called a scalar product. By the way, this is linear algebra, so this is very typical way to define something abstract. How did he define a vector space? We started with a non-empty set, and we assumed 8 conditions on addition and scalar multiplication, and that thing was called vector space. And then there were many examples of vector spaces, and we went through many of them. Remember? Another example, we consider a map from one vector space to another, but we imposed 3 conditions. And when those 3 conditions are met, we call that map a linear map. And then we went through a number of examples, and then we studied all those kind of things. Similar thing is taking place here. We have a double variable map from V2 to R and 4 conditions. If these 4 conditions are met, then that double variable map will be called a scalar product. And then, of course, we're going to go through a number of examples associated to that. Now, let's scrutinize these conditions. But before that, some notation issues. Some people prefer to use these triangular bracket expression, but some people prefer to use this dot product expression. Which is better? Well, I'm neutral. Obviously, our textbook author prefers this way. That's fine. But over the years, I found that most of my students preferred this way. And the students who are doing these usually outperform the students who are doing these. So, okay, in this notebook, I'll follow the second notation a little bit more closely. But here, we are doing it for the first time. We are learning it, so I'm going to do both. Okay, ready? The first condition, symmetric. Scalar product V, W is equal to W, V. We can switch the order. Or if you look at it in the second notation, V dot W is equal to W dot V. So symmetric, we can switch the order, or commutative. Now next condition, bilinearity. Let's look at the first line here, and then the first line there. Please note that the second component is fixed as W. Fixed as W. Now if you look at the first component, what do you have? V1 plus V2, and that's separated. Addition is separated. Let's go over here. We have scalar multiplication C times V, but now that's separated out. So the second component is fixed as W, and with respect to the first component, we have linearity. Addition is separated, and then scalar multiplication is separated. If you look at the second line, exactly the same thing is going on to the right-hand side. The second component is linear because we can separate the addition, as you can see here, and scalar multiplication. So we have linearity in the first component and also the linearity in the second component. That's why it is called bilinear. And that's a conclusion I can draw from the left-hand side, a little bit more traditional way. Now, if you look at the right-hand side, then it doesn't look like linearity or bilinearity at all. It looks far more like a distributivity from the right-hand side and the distributivity from the left-hand side. How about these? Kind of like associativity of multiplication, and that one too. Even though this multiplication, scalar multiplication, and that multiplication, scalar products, are actually two different multiplications, but still it looks kind of like associativity, and that's fine with me. Maybe that's why students prefer the second expressions. They resemble the traditional algebraic rules a bit more. Let's look at the fourth rule, the positive definiteness. The scalar product of itself is greater than or equal to 0, and equality equal to 0 if and only if we have a 0 vector. That's a property, but another way to write the same thing is this way. V dot V is always greater than or equal to 0, and if you multiply the same thing twice, then it's square, and in real number arithmetic and pretty much everything else, square is always non-negative, isn't it? And equal to 0 if and only if you have 0 vector. So yes, this too resembles the traditional algebraic rule. Maybe that's why students prefer to write inside these dot product notation over these bracket notation. Maybe that's the reason. I'm just speculating. In any case, because most of the students did better when I did this way in the right hand side, I'll try to follow this way, but our textbook is written in the triangular bracket way, so be careful, and you may have to put some effort to it. Okay, so much for definition. Now let's go over to the next topic, the bilinearity that we talked about here as two separate conditions, addition and scalar multiplication, can be reduced into or combined into a single condition using linear combination. So instead of separating as addition and scalar multiplication, put those together as linear combination for first component and second component and call it as bilinear, linear on one and linear on the other. Bi means two, right? And that's another way to define the same thing, and that's equivalent. And the proof of equivalence is left to the students. The other conditions, symmetry and positive definite, they remain the same thing. Now, before going over to examples, let us go over to example. Yeah, why not? Example of scalar product. The most typical example is a traditional dot product. Vector x1 through xn, dot product y1 through yn, just x1, y1 plus x2, y2 plus all the way up to xn, yn. Just multiply each component together and then add them all up. The traditional dot product. Now, do you recall going over the proofs of, let's see. Yes, these conditions in the right-hand side with respect to this? Have you done it before? Yes, you have in week 2, and depending upon semester, maybe in week 1. Yes, you must have done it. So yes, it is an example of a scalar product. Another example of scalar product, well, you can multiply scalar product of two functions, f and g, by integral from a to b f of x gx dx, when f and g are, well, yeah, okay, and that's just, this scalar product when v is a space of continuous functions. Let's see, f and g are already selected, so I must go to some other character. Oh boy, I'm kind of running out of character here. And then Okay, that'll do it. If you define your vector space as the space of continuous functions from the closed and bounded interval ab to R, then each function that belongs to this capital V has well-defined integral from a to b. And then same for g. And then, of course, integral from a to b f of x, g of x dx is well-defined. Okay, we have well-defined integral. Now, does this integral satisfy these four conditions? Symmetric? Oh, that's easy. Bilinearity, can I separate the additions? And then can I pull out scalar multiplication? And finally, the positive definiteness, that too is trivial because f squared is always non-negative inside the integral. Anyway, yes, you can prove it. The detail is left to the students. Here's an interesting example. Because I already used up this notation dot, I brought up another example, so I had to make something else. So I brought up the star expression. So x1, x2, x3, x4 star y1, y2, y3, y4 as x1, x2, x3, x4 as row vector and a certain fixed matrix and the column vector of y1, y2, y3, y4. Define it like this. And then can you prove all these four properties? Symmetric. Switch x and y's, and then can you prove that if we switch x's and y's and then do the matrix computation, do you get the same thing? Well, you're going to have to do some brute force matrix computation, but it'll turn out the same. How about these properties? If you have, let's see, x1, x2, x3, x4, and then we have to add another vectors, and you're going to run out of characters here. Y is already here, so why don't you add z1, z2, z3, z4, add them up, and then use the appropriate matrix multiplication or matrix algebraic rules and then prove it. Yeah, it's not going to be too bad if you write those down. Bilinearity 1 and 2, maybe a bit tedious, but no problem there. It's just a matrix multiplication. Let me mention a little bit about the fourth property, the positive definiteness, because that's the only one that deserves our attention. So multiply the same thing, x1, x2, x3, x4, and then x1, x2, x3, x4. And then by definition, we have row expression and column expression, and we have the matrix, same matrix before. And then what choice do we have? We actually have to do this matrix computation. So let's do this matrix computation, these two. And I did only first two rows and then the other I just left as dot, dot, dot. After all, details left to the students. And then further computation, okay, I got tired of it. So I did only the first times first and then left the others as dot, dot, dot. So we have to do some tedious computation. But then again, what you need to do is do some algebra here and then express all those in this form. It'll turn out that way. It'll turn out that you're going to end up with something squared, something squared, something squared, and kind of like that. So that this is always greater than or equal to 0. And when do we actually have 0 equality? Well, each of these complete square must be 0, right? So if you look at each individual inside and then set those system of equations that turn out to be something is equal to 0, another is equal to 0, and the third is equal to 0, the fourth is equal to 0, and then work those out, you're going to get nothing more than all zeros, x1, x2, x3, x4, they're all zeros. Well, It's going to be extremely tedious and unpleasant computation, but it's doable. I didn't make up my mind whether to assign this problem as a homework problem or not, but I may. If I do it, then the others, these 1 to 3 are going to be just a bit tedious but elementary. But the fourth condition will be elementary, but not just a little bit tedious. It's going to be highly tedious and extremely unpleasant, but it'll work out. Now, among these examples, of course, by far the most important is this one, isn't it? So let's talk a little bit about these. Let's go back to the review, something we discussed way back in week 1. In two-dimensional case, we define the dot product like this, right? That's because we already had well-defined angle concept. In abstract vector space, we don't have an angle, so we cannot define it like this. But in Euclidean space, yeah, we do have angle, so you can define it like this. And why do I have cosine? That means you want the contribution in the other vector's direction. And then it is possible to do the computation using multiplying the first component and second components together and then adding them up. How do you prove it? I think I left this as a homework problem set in week 1. Goes kind of like this. We have a triangle and then apply the law of cosines. Kind of like this. And what we have, 2 times size of v1 times size of v2 times cosine of theta. Wait a minute, this is nothing more than the dot product. So you can solve with respect to this dot product. Flip the other 2 to the left-hand side and divide by -2, and you get that. And then do some algebraic computation. By Pythagorean we have this, Pythagorean we have that, and by Pythagorean we have this, and break up these complete squares and do some cancellation. All the x squares and y squared, they'll be all cancelled out, and then what's going to left? What we have left will be precisely what we wanted. Even if you have n-dimensional case, the definition is the same. By the way, same picture, but not restricted in plane, kind of tilted in arbitrary dimensional space, but still, size of v1 is nothing more than Pythagorean. Size of v2 squared, nothing more than the Pythagorean, and same thing here, Pythagorean. If you break up all the complete squares, then you get minus 2x1y1, minus 2x2y2, minus 2x3y3, and so on, minus 2x and yn, all those. And all the squares just cancel each other out, and this negative, negative, and then 2 and 1 have canceled out. In the end, you get what you want. A little bit tedious, maybe? Not even tedious, actually. No, not even tedious. No. All I have is a bunch of dot, dot, dots. What's the difference between this proof over here and that proof over there? Just some dot, dot, dot. No. So it's not tedious. So what did he do? It's not a sketch of proof. We complete it, as a matter of fact. All right. And then as for the angle concept, okay, we have cosine of theta. And then when do we have dot product equal to 0? When do we have cosine of theta equal to 0? Of course, that's when we have right angle. So this is a conclusion we can draw. When you have dot product equal to 0, then we have orthogonal or perpendicular. And this is a starting point of the perpendicularity. That's going to be the topic of the next section, by the way.